In this video, we're going to discuss about Z-transform, which is used to find the frequency domain representation of discrete time periodic signals. So it is a counterpart for Laplace transform. So Laplace transform was used to find the frequency domain representation of continuous time periodic signals. So here, when the signal is in discrete time domain, we can use Z-transform to find the frequency domain representation, and it is very useful tool for signal analysis in digital signal processing, and it is very easy also to understand the representation from using the reference of Laplace transform. So this is the equation for Z transform. Xz is equal to n is equal to minus infinity to infinity for an infinite length sequence xn. You can write like this, and z to the power minus n is the kernel here. So earlier in Laplace transform we are using e to the power minus st, which is replaced by z to the power minus n. So what is the ROC here, region of convergence? The range of values of z for which the above equation is defined gives the ROC of z transform. So the value for which the value of z for which this equation is defined is known as the ROC for this z transform. So generalization of z transform. So if we take a continuous time signal like this xt and versus t, so if we sample this continuous signal at discrete time intervals 1 2 3, like after every 1 second, if we take one sample, then we get discrete time signal. So if this is a discrete time signal, then we can write xt as a sequence of the original signals amplitude x, this amplitude at the interval, suppose x0 at t equal to 0, x0 value will be here, and it is multiplied with del t. So del t is defined at t equal to 0, so it is 1 at t equal to 0. So that is why we can write like this: x0 into del t, then the first sample x1 into del t minus 1. So del t minus 1 is the shifted version of del t at defined at t equal to 1. At t equal to 1, del t will be equal to 1. So you can write this x1 into 1. So this is the representation at which position the sample is there. We can write like this: whichever the position is there, at that we take a this impulse signal and multiply with the sample amplitude at that point. So if we write it in a generalized form as using the sum term, then you can write from n is equal to 0 to 9. Here 9 sample is there, so xn into del t minus n. So n is the position, so these are the values of n, suppose in discrete time 1 2 3 4. Okay, so if this sequence, if we assume that it is lying from minus infinity to infinity, then we can also write the above equation in a form of like this: minus infinity to infinity xn del t minus n. So n is the time interval, discrete time value, like this in the right hand side, positive values, in the left hand side, negative values. So this is the first form of generalization for Z transform. Okay, so if you assume that this delta signal is a train like this, where it has impulses at every t, like if we say that the sample time is fixed and it is equal to capital T, then every capital T we are getting a impulse. So this del t minus n can be, as a whole, we can express like this sequence of impulses. Okay, so this block diagram representation also gives this equation representation, like if xt is coming and we are multiplying with the impulses at that point. So if we multiply these two, we will get xt into del t minus del t. So if you take the next sequence, suppose at t equal to 1, you will write x1, and here you will use del t minus 1, del t here in the bracket, within the bracket you will use t minus 1. Then for x2 you can use del t of t minus 2. Like this you can get the impulses, and you can multiply with the same pole value at that point, and you will get like this. So if you add all these outputs, and you will get can write like this. So this generalized from here we can write like this. So x and t, so x and t will be the value for different position of n, and this del t minus nt is the as a whole representation for this one impulse function. So if you take Laplace transform of this equation now, so this equation is written based on this equation. Okay, so now we are taking Laplace transform from this equation. So from the this side, this time domain signal becomes Laplace transform output is xs, and here we know that this is the function, so this is the signal. So if we take Laplace transform, we have to multiply it with e to the power minus st. It will be like this, e to the power minus st. So e to the power minus st is here, xt instead of t we are using nt, so we have to write nt. So e to the power minus st. So this is the signal, and Laplace transform of del t is 1. So if you simplify this, you can write xs is equal to this n is equal to minus infinity to infinity x and t e to the power st whole to the power minus n. So if you take this e to the power st as equal to z, then we can write this as z to the power minus n. And if we take capital T is equal to 1, then we ultimately get like this. So this becomes z to the power minus n, z becomes xn. Then we can write here e to the power st, we are writing as z. So here we can write xz is equal to summation of n to equal to minus infinity to infinity xz z to the power minus n. So this is the final equation for t is equal to 1 and z is equal to e to the power st. So here this capital T is sampling period or sampling time, and it is equal to 1 by fs, where fs is sampling frequency. So this sampling period you already obtained in these discrete time signals. So it is the time period after which we take a sample for continuous signal to get the discrete time signal. Okay, so we want to relate this Laplace transform and Z transform by finding a relation between the S plane and Z plane. So S plane is the field representation for Laplace transform output, and Z plane is the plane where we show the Z transformation output. So we know that Z is equal to e to the power st, as considered here. Z is equal to e to the power st. So for Z transform we consider this e to the power st equal to z. Again, s is equal to sigma plus j omega in Laplace transform. So if we put this value of s here, we'll get like this. So you can separate this like this, e to the power sigma t into e to the power j omega t. So now if you want to write this equation in a polar form like this, r e to the power j omega, then you can write r e to the power j omega in the left hand side in place of z. Z is equal to this. If you put it here, then you can compare with this. So this results in r is equal to e to the power sigma t, and this omega equal to omega t. So this omega is your angular frequency, is equal to 2 pi by t, and this omega is discrete frequency. Okay, so they have relation like this, omega t, omega is equal to omega t. Okay, so this is time sampling time, and this is angular frequency, and this r is the radius for unit radius of the circle or ring which Z transform will be using. Okay, so this is the r, this is your e to the power j omega t. So this is these two terms are used, this omega and r are used to represent the circle in the Z domain corresponding to the Laplace transform output using sigma. Okay, so Z domain basically represents a circle with radius r. It represents Z domain represents a circle with radius r. So r is given as e to the power sigma t. So if the Laplace transform is given by this representation, where there we have two poles at sigma is equal to -2 or sigma is equal to 4, Then we can show that Laplace transform S plane as like this, and corresponding Z transform representation in Z domain will be like this, where this pole at sigma is equal to 2 corresponds to a unit circle with radius r is equal to 2, and this pole at sigma is equal to 4 corresponds to a unit circle with radius r is equal to 4. And the reason of convergence, where like earlier we were assuming that sigma greater than -4 or sigma less than -4, sigma greater than -2 or sigma less than -2. Now you would consider a circle and like this, so 0 less than or less than 2 is stable. So if the ROC is like that, if the circle with radius 2 and the points are within the circle, then you can say this output will be stable, that transform output will be stable. Like this, the ROCs are defined here in terms of the circle or ring. Okay, so if you see that here r is equal to e to the power sigma t, if you put the sigma equal to 0 here, it becomes 1. R is equal to e to the power 0 is equal to 1. So this sigma equal to 0 represents the imaginary axis. So at imaginary j omega axis we get r is equal to 1. That means this imaginary axis is represented by this unit circle with radius 1. Okay, and if there is a pole at infinity, then that can be represented by the is point 0. That is, it will not indicate any circle, it will be referring to the point 0 in the z domain. Okay, because at infinity we are getting r is equal to 0, so its radius is 0. That means a circle with radius 0 is nothing but the origin point 0. Okay, so this is the reference. Like this, if a pole is at infinity, we indicate it by the 0 point here, and if there is a pole at finite distance, so then it will be a unit circle at with radius r given by this sigma value. Okay, uh, the region of convergence of xz consists of a ring in the z-plane centered about origin. So that is what we are discussing, that the ROCs are a circle surrounding around the origin point in z-transform output in the z-domain. Then existence of a z-transform. So if z-transform existed, we can say that magnitude of xz should be less than infinity, then only we can say that z transform exists. Then if you put this condition formula here, z transform xn is equal to z to the power minus n, then we can replace z to the power minus n by r e to the power j omega. So z is equal to r e to the power j omega, where we could replace omega t here, then we get z is equal to r e to the power j omega for t is equal to 1. Okay, so from that we can obtain this equation, r e to the power j omega. This omega is different from this omega. We are getting this omega by putting n t equal to 1. Then we can say that this e to the power j minus omega n, its magnitude will be 1, because we know that e to the power j theta is equal to sin cos theta plus j sin theta. So that's magnitude will be ultimately cos square theta plus sin square theta will be equal to 1. So that's why this term is made equal to 1, and we are getting this expression. So this is the condition for z transform to be stable and or z transform to be exist, where r is the radius or the of the circle of z transform output. Okay, therefore the value of r for which equation 1 converges is known as the ROC of z transform. And this is the equation of z transform. If we put z is equal to r e to the power j omega here, then we get like this. Okay, so if we take r is equal to 1 in this equation, then we can write x e to the power j omega equal to this r is equal to 1 becomes this r to the power minus 1 will be equal to 1. So we get this equation. So x e to the power j omega, this side xn e to the power minus j omega. So this equation is known as the discrete type Fourier transform, and it is commonly used in Fourier transform uh, to find a Fourier transform of discrete signals. using this equation. It is very important equation. So this we can get to this equation from Z transform also.